All right, so what I want to talk about is this blood age trivia stuff. How this is tested. It's confusing. It's scary. People feel intimidated by it. It's not well understood most of the time, even by people who are teaching it. I've got a couple of different ways to remember it in my books. And, I sort of blow off the idea of trying to reason your way through it. But I'm going to change my tune on that slightly because I think it's valuable if you can understand it for a couple of reasons. One, it makes it harder for you to be tricked on a multiple choice question. Two, it helps review some other adjacent topics that the better you understand them, again, the harder it will be to trick you. Now, these questions are almost always shown with brain MRI. The reason is the physics and stuff for this, like, aging blood doesn't really follow the same rules other places in the body. And you don't really need to understand why. Just know that blood age stuff is it's for the purpose of multiple choice, it's only going to be shown in the brain. And the only two sequences you need to worry about are T1 and T2. So this right here is probably the most common phraseology for the question. Now, we're going to go into detail understanding this stuff, and then I'll come back to this question, so don't try to figure it out right now. But I just want to point out a couple of things on how this can be asked. So this is probably the most common, is this terminology of hyperacute, acute, subacute, late subacute, chronic. Those are words that people who write multiple choice questions like to use. Those are words that are all over the radiology literature. Some other ways they could do it is by giving specific time frames in hours or days. And then you have to know, well, which one of those is hyperacute or subacute. The other way that they can do it is they can actually ask what the change with the red blood cell is. Is this oxyhemoglobin giving this signal or deoxyhemoglobin, etc., etc.? And the last way, which is probably the least common, would be to ask a real specific physics question like, is this because of T2 star effect or something along those lines? So as we go through this material, sort of the four things that you need to know, five, you need to know what the color changes are as the blood ages. You need to be familiar with this terminology, the hyperacute, subacute, late subacute stuff. You need to know the hours/days that correlate with that. And you need to know the changes in the actual red blood cell, like the actual physiology portion. And then you need to know a little bit of the physics. The more you know, the better, because it sort of translates into other stuff. So this is the way this topic is typically taught in residency. Sort of, you've got a PhD guy that comes out and he says, I'm gonna break this down and make it simple, and then and then starts to do that. I'm going to try not to do that. I'm going to try to sort of use general concepts to sort of make it so it's a little bit easier to understand. Math's not necessary. All right. And to get there, we're going to have to review a couple of topics here first. I'm going to introduce some fancy physics vocab words, and then we're going to go back in time and review what susceptibility is related to T2 and T2 star, why stuff is T1 dark. I'm going to use water as an example, and then we're going to talk about blood physiologically, and then we're going to go back through all of the different physics and tie it all together. And hopefully, it is my goal that you won't have to make baby noises or anything like that anymore, that you can actually understand it. So let's start out with the fancy physics vocab. Now, the first word that I want to introduce is susceptibility. What does that actually mean? So susceptibility is a measure of the extent to which a substance becomes magnetized when it's placed in an external magnetic field. So, something like that. So maybe a better way to think about susceptibility is this. Magnetizability. Like that would be a synonym for susceptibility. So as a review, in the absence of an applied magnetic field, the magnetic movements of hydrogen nuclei are going to be randomly oriented. And then when you apply the field, the B0, you're going to have them align, or majority of them align in a specific direction, with the magnetic field. So let's imagine that in this sea of protons, that you've got the magnetic field applied against this tissue, that you've got a specific kind of tissue that is susceptible to being magnetized. So that could be a piece of metal, like a gallbladder clip, or maybe the surgery resident left a wrench inside the patient. So let's imagine that we've applied this our B0, right, which is always on, right? The magnet's always on, through this particular tissue. Within that wrench, an internal magnetization or polarization is going to be created, and it's going to have a choice. It can either oppose the direction of the main magnetic field, or can augment it. So here's the vocabulary. If the polarization opposes the applied magnetic field, the effective field within the object is reduced a little bit. And the lines that they'll draw, like in the diagrams for this kind of stuff, they sort of squish out. They're dispersed. This is called diamagnetism. Now, that is when the stuff lines up against the field. Now, when it lines up with the field in the same direction, augmenting it, there's a couple of different vocabulary words that you'll see: para, superpara, and ferromagnetism. And the reason you would use one versus the other is how strong that opposition is. So just sort of to put that in relative perspective, para, if you thought of para as like a 1, super is like 1,000, and ferro is like a 5,000. So there's a big step up there. And it's along the spectrum. Now, most things in the body, biological tissues, are actually weakly diamagnetic. And it's on a spectrum. Water, fat. Calcium is actually the strongest diamagnetic substance in the body. It's sort of why you see signal drop out, like along the cortex of the bone, etc. Now, that's most of the stuff in the body. Now, there is a minority of tissues in the body that contain accumulations of metal, copper, manganese, iron, a little bit of iron, right? Like maybe some red blood cells. Gadolinium actually works by being paramagnetic. Air, why would it air be? Because oxygen actually acts weakly paramagnetic. And then you've got some other things in the body that we're going to talk about also, ferritin and hemosiderin, that have an even stronger augmentation of the magnetic field, and they're considered super paramagnetic. And then there are foreign bodies like iron and steel, like the gallbladder clips and stuff like that, that will show up in a scan, and they are extremely ferromagnetic. So like the effects that we're going to talk about related to this will be exaggerated to an even more extreme. So those are our fancy vocab words. Now let's pivot back to this idea of T2 and T2 star. So just as a refresher, we've got our tissue, it's in the magnet's always on, it's aligned, the net vector is aligned with the main magnetic field, and then we strike it with an RF pulse here, and that knocks it down. And when we're talking about T2, we're talking about the transverse dimension, this one here. And when it first gets knocked down, all of the, this is like a sum here, right? The arrow is not just one arrow, it's a bunch of little arrows sort of added up in that direction. They're lined up for some period of time. So we'll look at it like this a little bit easier. And then over a certain period of time, they start to get out of order. They dephase back to randomness here. And that's T2 decay. So you often see it sort of diagrammed out like this, right? More and more and more and more and more sort of out of sync with each other. What causes this T2 signal to, what actually causes them to get out of sync like that? Why does that happen? So there's two main reasons. You've got an inhomogeneity within the external field, and then you've got inhomogeneity within the local magnetic field, within the tissue themselves. So you may remember this here also, where this is like the hypothetical T2 decay, but then you've got this T2 star, which is sort of like random causes plus your fixed causes. So it's not just the tissue spin interactions, which you think about with the pure T2, like one being a little bit different than the other. It's that plus field inhomogeneity that actually causes the T2 star to be more rapid than the actual, just signal-on-signal crime. So maybe a better way to think about T2 is like this. So imagine that we've got a track team here, and these guys are from, I don't know, Jamaica or Kenya or something like that. And they're three twin brothers here, identical in every way. And they're going to start on the starting line together. And they're gonna go around. Well, they're gonna stay right next to each other, right? These guys are identical. They're gonna be staying right next to each other for a while, and then maybe one of them just happens to train a little harder than the other, and the other guy he had Taco Bell for breakfast, and that was just a bad idea, and so he starts to lag behind. The other guy starts to pull ahead, and the other guy's in the middle. And then, so even though they're pretty similar, eventually they begin to dephase. But that happens more slowly when things are very homogeneous. Now, if you've got three different guys from three different teams and backgrounds, etc., and they all start on the starting line together, they're going to separate out from each other really fast. So the point of this is to sort of help you remember that things that are heterogeneous are going to lose that T2 signal faster than things that are homogeneous. So maybe making an attempt to bring this together with the prior topic. Here's our B0. We'll have two B0s here. And one of them is totally homogeneous. It doesn't have any local tissue that's creating susceptibility, versus the other one that has like speckles of tissue that are capable of being magnetized and then either opposing or augmenting the magnetic field, in this case augmenting it. So where these guys were homogeneous, this is heterogeneous, right? So if we look at our diagram here, the homogeneous ones are going to be like the yellow here, like the regular T2, and the heterogeneous stuff that's got augmentation focally, different little tiny spots, is going to be the orange. So that's going to be like, and the more heterogeneous it would be, the stronger that T2 star effect would be. So when you've got something that is homogeneous, you're going to see some, homogeneous, slower dephasing, more signal, T2 bright. And then the opposite is true. Heterogeneous, faster dephasing, less signal, T2 dark. So where I'm going with this is, if you've got a lot of susceptibility, you're going to augment that T2 star effect because it's more heterogeneous, and then you're going to become T2 dark. All right, now let's move on to review the topic of T1. So again, quick review here. We're lined up with the field. We get struck with our RF pulse. We get knocked down in opposition to it, and then we're going to build back up. So for the longitudinal signal, which is the T1, right, to recover, we've got to take protons that are in, or spins or whatever, that are in a high energy state and put them in a low energy state. Well, what do I mean by that? High energy state is the state where they're opposing the main magnetic field. That's considered high energy. How did they get high energy? They got energy transferred to them from that RF pulse. Now remember, you can't create or destroy energy, right? That's one of those like basic scientific laws. So you gotta do something with it. You gotta give it back to somebody. You can't just throw it away. You gotta give it back to somebody. So if somebody handed you the gift, you can't just pitch it in the dumpster. You gotta hand it back to somebody. Who are you gonna give it to? Well, usually what happens is that it's a transfer of heat. Now, it's not a lot of heat. You're not cooking people in the magnet, right? But that is how, it's this energy transfer into the lattice. It gives off that energy and heat. And as it does that, you start to turn them more and more and more from that high energy state into the low energy state, and that is considered recovery. That's T1 recovery. And you'll see, it graphed out like this typically, right? So, and again, if you've got something here, and that's how we define T1 signal as the recovery to 63% of its potential. If you get something that does that quicker, like that, it's considered it did it quicker, so it did it shorter amount of time to do it. It got T1 shortened, that's brighter. So when people say, and there's intrinsic T1 shortening of the pancreas, it means it's bright. It's bright. It's bright on its own. Gadolinium works by shortening T1 effect, right? So that term shortening for T1, if you look at that, how it backed up, more signal, gets to the 63% faster, and that's what that means. So why would one type of tissue be better than another type of tissue at doing that? Well, remember I said it's all about giving heat back? So tissues that are efficient at transferring energy as heat have really short T1 times, and tissues that suck at sharing their T1 heat have very long T1 times. So, like large stationary things have low vibrations, and therefore they are very efficient at giving their energy back. Whereas something like water has a high vibration, and therefore it is terrible at giving back its energy. And we're going to talk about why in a second. But I want to drive home this idea of sort of movement and heat being the same thing. Think back to whatever, basic chemistry or science or whatever, when you learned about like what heat actually was. Remember, it's how fast stuff is moving is what makes it hot, right? So like theoretical absolute zero, like nothing, it's like complete stopping. That's why there is an absolute zero, because you can't slow down any more than being stopped. Whereas you can just get hotter and hotter and hotter and hotter and hotter, because things can move faster and faster and faster and faster and faster. So it's just how fast things are is how hot they are. And for them to become cool, they have to slow down their movement. Which means for them to slow down, they have to make something else speed up a little bit, because you can't destroy energy. It's always just being transferred. So I guess another way to look at it would be, water is bad at sharing. It doesn't want to share. And it's because it's moving. It has a high vibrational frequency. Well, what does that mean? So let's look at the molecule of water. Remember that it's two hydrogens and an oxygen. And I like to think about the oxygen as like a jealous lover. And it's got a pull on its two wives, the hydrogens here. And that pull creates like a little polarization here, right? It's polar. And the pull on the hydrogen electrons, supposedly, I think about it, I guess there's a couple ways to think about it. One would be to think about it like a top that's uneven, spinning, how easy it would be to spin, that kind of thing. Another way to think about it is that when it pulls the electrons like towards it, it's exposing the hydrogen nuclei. So when they get hit with a pulse, it really spins them. It was highly susceptible to that. So it spins very fast. And remember, because of that, and this is I'm gonna make this matter later, that this spinning is the reason that it's not good at transferring its energy, and therefore it has a long T1 time, and therefore it's darker on T1. All right, so rapid review here of the stuff we talked about. So remember that susceptibility basically just means you're going to either oppose or align with the field. Less homogeneous things create a loss of T2 signal, amplifying that T2 star effect. And the pull of oxygen on hydrogen sets it up to hold on to its heat longer in that water molecule, and therefore recover the T1 signal slower. All right, so the last thing here, we did it almost, is to just sort of review the physiology of blood and then bring all this physics together in a way that it makes sense. All right, so we first need to talk about what blood is. Now, remember that blood is made up of liquid and cellular components. The liquid part is the plasma, It's just pretty much can be thought of as water. It's not quite water, but you just pretty much think about it as water. And then the cellular portions is all the other crap that's in there. But, you can think about it as basically red blood cells for the purpose of blood changing. Obviously, there's platelets and white blood cells and all that other stuff in there too. All right, so let's talk about the red blood cell for a second. So the whole point of the red blood cell is to do what? It carries oxygen, right? And the way that it does that is by using a glue, hemoglobin. Now, sort of in the life cycle here, it changes, right? So we've got, this would be oxygenated hemoglobin. And then, it's going to shed its oxygen. And then it becomes deoxygenated hemoglobin. And then after a period of time, breaking down, like in the clot, it's going to become methemoglobin. And we'll talk about the difference, what that means in a second. And then, eventually, the hemoglobin gets broken down into fragments or chunks of iron proteins called ferritin and hemosiderin, sort of like that. And the difference between these two things, I sort of mentioned earlier, but I'll just recap it, is that the ferritin and hemosiderin is super paramagnetic, as opposed to the methemoglobin, which is pretty strongly paramagnetic. So how super is super? You may remember it's like 1,000 times more. So it's a big difference. All right, so here's our brain. And we're going to get a bleed now. So just schematically here. Now, when arterial blood extravasates in this like hyperacute setting, over 95% of the hemoglobin is still in an oxygenated state. And because of this, it's like most tissues in the body, it's very, very weakly diamagnetic. And you can think about the structure of the clot at this point. It's probably easiest to think about it as basically just being water. And because it's water, it has signal that's sort of predictable, where it's going to be T2 bright a little bit, and it's going to be a little bit on the darker end for T1, maybe ISO. Well, it's not quite water, right? But it's like I said, there's other stuff floating in there. But I start my brain sort of thinking about it like it's water-ish. A little bit on the T2 bright end, a little bit on the T1. It's not dark, but it's ISO'd on the darker end. So this here is our oxygenated hemoglobin. And within a few hours, that oxygen is going to begin to dissociate from the clot's hemoglobin. And when it does that, we make a change from being oxyhemoglobin to deoxyhemoglobin. And the main thing that's going to change there is now we have 4 unpaired electrons. And that is going to result in a change from being diamagnetic to paramagnetic, actually pretty strongly paramagnetic. Now, just sort of as a review here, remember, now we've got some heterogeneity within that local field, right? There's a little bit of speckles of susceptibility augmenting that local magnetic field. And because in this state that it's still concentrated within the red blood cell, it's sort of like it's strong enough there to actually create a signal change. So just reviewing here, instead of having that normal T2 curve, we're now dropping into the more exaggerated T2 star effect, which is going to result in heterogeneous field and then therefore faster dephasing, less signal, and darkening of the T2 star. So at this point, we're going to change from being T2 bright to T2 dark. Now the T1 signal is going to be the same in both hyperacute and acute stages. So this is what he considered the acute stage. Now the next thing that's going to happen is there's going to be a continued breakdown of the blood product. So we're going to change from deoxygenated hemoglobin to methemoglobin. Now, methemoglobin has 5 unpaired electrons, and that is going to mean that it's even more strongly paramagnetic. I sort of like drew the color changing here, but let's take a more in-depth look. Okay, so we've got a more detailed look here, and we've got oxygenated hemoglobin here, their oxygen here, and that'll leave, right? And now we're in our deoxygenated hemoglobin state. And I want you to notice that we've got our iron here, and it's in a +2 state. And then when we make our change over to methemoglobin, it's now in a +3 state. And you may remember this thing like methemoglobinemia, the chocolate-colored blood was like the step 1 buzzword. Well, the reason that was a thing that was bad was because this can't bind oxygen. Instead, it binds water. So who cares, right? Well, that close proximity of that oxygen molecule, remember we said he was the jealous lover to this iron, is going to alter the way he operates and does business, because now he's sort of like, he's around a real alpha dog now. And so it demasculinizes him. He's now going to act like a beta male. And we're going to talk about why that matters here in a bit. Oh, sorry. That histamine needs an extra hydrogen there. All right, okay. There we go. So remember I said that oxygen is like the jealous lover, and it pulls the electrons of hydrogen close to it. Well, when it gets in close to the iron like that, something magical happens. And people who pretend to understand this stuff call this an inner sphere relaxation. So basically, what happens is it chills that oxygen out. That interaction right there makes it so that it's not doing that pull thing as much as it was before. And it doesn't just happen there. There's like a cascading effect where it sort of spreads to all the local water right there. So they all sort of chill. And now they lose that fast spinning that they were doing. They're not doing that anymore. They spin slower because they're not top heavy, and they therefore transfer their heat better, and therefore their T1 time is faster. Then they become T1 bright. And that is the reason why at this stage, which is now the subacute stage, that blood becomes T1 bright. It's because of that interaction of the water molecule with that methemoglobin, as opposed to the interaction that it has with the deoxygenated hemoglobin. That's the change, and that's why it matters. So late in the first week, you're going to have lysis of the red blood cell. And as that occurs, the methemoglobin is going to spill out into the extracellular space. So everything that we've been talking about before this happening has been intracellular. But now that red blood cell is getting older and older, it's been living in a clot for a week, and it starts to crack and leak. Now the significance of that is that methemoglobin that was strongly paramagnetic, that was creating that T2 star effect, is now going to leak out. And instead of thinking, and then it's going to, I think about it sort of like oozing and spreading around, something like this. And now it's less concentrated. So it's more homogeneous, and therefore there's less T2 star effect. So you're going to start to see the signal become brighter on T2 again. Now, the molecule itself is intact, still with those 5 unpaired electrons, still allowing that inner sphere bonding of water. So you're still having that bright T1 signal, but you changed your T2 signal because you lost that. You went from being real focally heterogeneous, clumped within the cell, to more homogeneous, spread around. So T1 stays bright. T2 becomes bright again. It's being more of the T2 and less of the T2 star. So in the final stages of hemoglobin degradation, we're going to end up getting that breakdown of methemoglobin completely into basically fragments of iron, hemosiderin, and ferritin. And these guys are no longer paramagnetic. They are super paramagnetic. So whereas before I said that the signal was sort of diluted and we lost that T2 star effect, now we're going to get it back, because remember, the difference between paramagnetic and super paramagnetic is like 1,000 times. So we're really going to ramp up that heterogeneity in the field, and we're going to really amplify that T2 star effect. The other thing that's going to happen is that we lost that methemoglobin that was allowing the water, to be nice about giving off its energy. So with that gone, we're going to make a change back from being T1 bright to T1 dark. So at the very end here, we're going to go dark, dark. So let's do a quick rapid review here. We've got our hematoma, and we've got our hemoglobins in its oxygenated state. And because of that, it's basically the same as other biologic tissues. It's weakly diamagnetic. So we're going to think about it as basically just the plasma, just the water. So that's going to be T2 bright, and then slightly iso on the, to slightly dark on the T1 end. And then after that, we're going to have our oxygen dissociate away. And now we're in the deoxygenated state, which, remember, makes the change from being weakly diamagnetic, same as sort of a lot of the other tissue, to paramagnetic. And now we're going to generate some heterogeneity, right? And because of that, it's going to amplify that T2 star effect, and that's going to have us lose our T2 signal. It's going to drop out. T1 is going to stay the same because we don't have that behavior of that water molecule is the same, right? Now, after a little bit of time, we're going to have the change to that +3 state, which is going to let the water molecule bind, and this is our methemoglobin situation. We're still intracellular now, and that's very strongly paramagnetic, which is still going to give us a T2 star effect, and it's still going to give us a dark thing on T2. But it's going to do something different with the water, right? It's going to mess with the water so that it spins in a way that it gives off its energy in a more efficient way. And then instead of being T1 dark, it becomes T1 bright. And then after about a week or so, the cell is going to start to break down and rupture, and that all that intracellular methemoglobin is going to bust out and sort of dissolve around and get diluted and become homogeneous again. And as that happens, we're going to have a more homogeneous field. So we've got all the runners that are sort of identical twins now. So that's going to bring us back to a regular T2 instead of that T2 star. And then we've still got the functioning methemoglobin molecule. It's just extracellular. Remember I said that that thing sort of diffuses around. So the water effect is going to stay the same, so it's still T1 bright. And then lastly, right, it's going to break down and be changed into ferritin and hemosiderin, and that's going to create that really strong paramagnetic effect, super paramagnetic effect, which is going to bring back, it's going to revive our T2 star effect and drop our signal back out. And we also, because the hemoglobin broke down, we lost our methemoglobin, which was the thing that was making the water protons be bright instead of their usual darker or iso configuration. So now we're in a dark situation. Now, the one thing that I left out here for completeness is that in the center of a chronic hematoma, you usually have some water content, and that will often make the center bright also. So sort of it becomes this pattern that we're describing in the chronic state is more of a rim pattern. All right, so here's a chart. You have to memorize this. As promised, here are the hours and days. Remember we said that it takes about a week or so for that red blood cell to break down. And remember, that's the difference between when you have your intracellular methemoglobin to your extracellular methemoglobin. Chronic, it takes, and that's a gradual process. That takes about 2 months. So chronic is just going to be the one that's the longest one possible. And the difference between hyperacute and acute, you can sort of go half a day, 1 day, 2 days, maybe would be one way to remember it. But regardless, you have to memorize this chart. Memorize the vocab words, memorize the times, and memorize the colors. Now, there are certain people, probably most academic centers, still teach the stupid mnemonic with the bit. IB, itty, bitty, baby, dude, ooh. It's embarrassing. So don't do that. Don't do that. If you have to sort of draw it out, I like this thing. This is the thing that's in my book. And, just sort of taking this like coiled approach. If you can draw this diagram, just draw it out once or twice. It makes sense. I actually think it's easier to sort of remember the mechanism now. Remember that thing's sort of in the middle. So let's take a look at this question again. So remember, the first thing you have to do when you're solving this is which one's T1, which one's T2. So T1, right, white matter is white on T1, and then T2, if you can get a little bit of fluid signal, that's nice. If you can't see that, then you want the white matter to be dark. Take a look at this thing. We're looking right there. And so what we've got is bright on T1 and dark on T2. All right, so we can look back at this. Good thing. There, it's right there. So knowing that it's bright on T1 right away makes you know that it's in that subacute / late subacute phase because it's bright on T1 because of the methemoglobin, right? It messed with that water molecule. And then we look at the T2 and we say, okay, it's dark. That means there's T2 star effect. That means that it's still really concentrated within the red blood cell. It hasn't been diluted out. So it's still intracellular. It's not extracellular yet. So now we're in the subacute phase. All right, I hope that was helpful. That's my best effort at teaching it. It's a complex topic. And okay.